So where are we on kind of more firmer ground is if we're using this in a predictive context, then it's a bit more clear because the question is more clear, all right? So you can ask very clearly, how good are my predictions? We can compare the observed value of y that we got to the predictions. And the only question that is left to answer is, how are you comparing these things? And we've already seen one good way to compare them that is very commonly used, and that's mean squared error. So mean squared error looks at takes the difference between the true value of y and the predicted value of y according to my regression model. And we square that residual, and then we take the average across our data set. So you could compare, if you want to you can look at your MSE, that tells you how good your predictions are in some absolute sense. But maybe if you want to measure in some relative sense, you can compare your mean squared error of your regression model to the mean squared error of a different regression model. So here, you might use different predictors. So I could have here, I might be regressing on age, and then here I might be regressing on age and BMI or something like that. Or add different interactions, other kinds of nonlinear effects that are in a different part of this lecture discussed there. So you can compare. And a very common comparison that people do is they compare their regression model with all of the different predictors in it that they're interested in to a regression model that is very, very simple. In fact, the simplest possible regression model that has no predictors. It's just the coefficient or just the intercept, which actually corresponds to predicting just the total sample mean of y for everybody. So I'll show you what I mean by that. So if you have here your data points and you regress, you do your regression model with this predictor. So you're going to get a coefficient for that predictor, and you're going to get an intercept. And maybe that's the fit you get. If you instead omit all of these predictors, that's like saying that all of these are 0, right? So they are not in the model, and you're only getting the intercept term, which here I've called alpha hat 0 to distinguish it from the fit that I get when I include all of these other things. So like the other coefficients we talked about in a, kind of the descriptive interpretation, the intercept will also change if you include predictors, generally speaking. And so here is so I've denoted that with a different letter so that you know that this is the one that you get when you include these variables, and this is the one that you get when you don't. And this is an interesting comparison because, like I said, it's the most basic possible regression model you could use. You have, in a sense, it's not even a regression. You're just the value you get here, this intercept value, is actually just the sample mean of y across all of these data. So I'm just not even looking at x. I'm pretending it's not there, and I'm just crushing all of these data onto one point, and I'm just taking the sample mean of all of those data points, and as opposed to this regression fit, which, like we've talked about, is kind of implicitly stratifying by a substrata of x, and then taking the kind of like a subgroup mean within each stratum. So that's not what it's doing mechanically, but that's one way to kind of think about what we would like it to be doing, right? So this basic regression model here, I've just written y bar and this is actually just stolen from Wikipedia. So here, this is the group mean, and then this is our kind of like regression fit. I've just taken these two lines, right, and put them in different plots. These little squares indicate the mean squared error of both of these. So if you know this, for example, this is the residual, right? So this is our y value here, and then this for this x, say this is x here. This represents our prediction function, right? Our kind of mu hat. We'll call this mu hat 0 of x. And so for this person, I'm predicting this value here. In fact, for every person, I'm predicting this value here, and that value happens to be y bar. And so this distance here is the difference, right, between our predicted value of x and the true value. And then the reason it's drawn here as a square is because if I square this, I'm getting the area of this square. And so you can think of the mean squared error as getting the area of each of these squares and then averaging them, or summing them, and then you divide by n. So if we're going to divide by n here, we're going to divide by n here. So you can think of it as a sum if you want, or as an average, it doesn't matter. So over here, it's the same thing. We have our residual, and we square it. And so the mean squared error, one nice way to think about it is like the sum of the areas of these squares. And what this shows you, one thing that this shows you is that if you have any kind of fitting at all, right, the mean squared error of the linear model will always be better than that of the constant model. So the constant model is like the dumbest thing, right? You will always improve. You will always improve by adding in a little bit of extra freedom and being able to fit a slope rather than forcing there to be no slope at all. So this thing is always better, and we can compare the two. We can compare the MSE over here to the MSE over here, and one common way of doing that comparison, you can look at the difference if you want. There's no problem with that. But conventionally, what people do is they look at this ratio of the mean squared error of your regression model divided by the mean squared error of this constant, okay? And they take 1 minus that ratio. And the reason for taking 1 minus that ratio is so that it works like this. So that this, so something to note, this will always, this thing which we call r squared, it's always going to be between 0 and 1. And the reason for that is because this ratio here, the mean squared error of my prediction model will always be lower than the mean squared error of my constant. And so this fraction is always a number less than 1. Both of these are also always positive. So this thing is less than 1 and greater than 0 because both numbers are positive. And the way that this behaves is that if my mean squared error, let's say these two things are the same. So my model is not doing better in mean squared error. It's exactly the same. It can't be worse, but it can be the same. Well, that means that these two things are, basically my model is not, my prediction is the same as this. And there is no difference in mean squared error, then this is 1, right? These are equal in mean squared error. That's 1. So we get 1 minus 1, and this is 0. So when this number is 0, that indicates that the fit is really crappy, basically. And if it's 1, that indicates near perfect mean squared error, near perfect prediction. So here's a case that it's not quite perfect, right? There's still some residual here. But perfect would be that it actually perfectly interpolates all of these points, and all of these points lie exactly on a straight line. And then we would get an r squared of 1 because this would be 0. So if this numerator is 0, this whole term is 0, and then we're just left with the 1 here. So that's people like r squared because if you're just looking at the MSE or a difference in MSEs or something like that, that quantity has a kind of scale to it, right? You can't always really compare between two different regression models, but r squared, because it's between 0 and 1, no matter what, then you can kind of look at two different cases and somehow compare them. But I still don't necessarily recommend doing that. There's really no point to doing that. And fundamentally, there are some cases for which it can just be fundamentally harder to predict than others, right? Because here, what you're measuring is both the quality of fit of the regression line to the data points, but also some measure of fundamentally how hard is it to predict these things, right? If y is inherently variable in each substratum of x, even the best prediction might not be perfect, right? What I mean by that is like, let's say that in this stratum of x, my y values are like this, right? So let's say that even if, the true conditional mean is here and we're nailing it, we have actually a very good estimate of the true conditional mean, we're still going to have a lot of kind of big residuals, right? Because y is just variable. And so this r squared may not be exactly 1. And that's not because the regression model is bad. The regression model is actually getting at the true conditional mean. It's because the true conditional mean is not all that's going on. There's also conditional variance, right? There's also this variability. And so the RMSE is kind of a combination. You're measuring both the how well your prediction model is fitting the data, but also how well the best possible prediction model could fit the data. And there's no way around that. There's you can't really distinguish the two. But it means that there's not really point between comparing r squared in one situation to another because that the conditional variance could be different. And so it's not that you're doing a better job at using regression. It's just that it's a harder problem, perhaps, right? Okay, so another interpretation of this is as percent of variance explained. And the reason is that this mean squared error, since this, I'll show you here, this mean squared error is my observed value minus my predicted value. But here my predicted value is just the group mean of y, right? The total mean of y. And then we're squaring that. And then we're taking the average of that. So this is exactly equal to the sample variance, right? This is just the sample variance of y. So if we replace these with expectations, maybe you'll see. So this is y minus expected value of y squared, right? And that's the variance of y. Okay, so this denominator here is an estimate of the variance of y. This one here, if you look at something called the law of total variance, and you make the assumption that your fit is really the true conditional mean, then this thing is actually equal to the expected value of the conditional variance of y given x. So you can kind of interpret this as some percentage of this total variance, and what you're left with, if you look a little carefully at the law of total variance, I'm not going to go through it. It's not totally, I don't think it's that useful. But if you go through it, there under these assumptions, you can kind of interpret this as how much variance is this model explaining out of the total variance. And I mean, I think that's okay, but there's no need for this, right? You don't really need to go that far to kind of stretch the truth a little bit to say this, because I think this is a perfectly interpretable quantity as just a ratio of mean squared errors, right? You're just the way that we got here, right? We're just, how good are my predictions? Well, look at the MSE and then just benchmark that with some very, very simple model. But you could also, to generalize this, like R squared is like a thing that everyone knows about, but there's no reason why this is privileged, right? You could compare the MSE of your model to something that's, a bit more sophisticated than this, and see, is this improving over something that, some kind of baseline that is a little more sophisticated than just a constant, right? There's no reason to look at just this. But I need to explain this to you because it's all over the place, okay? How do you do this in R? It's quite simple. So here I've generated some data set. I run a linear regression, and here I'm putting in all the relevant predictors that I want to include. This is everything that I've measured. I could also do just height or just weight. That's fine, whatever. I'm just going to calculate the R squared for whatever model this is. So then my M0 here is my linear regression where I'm just including the intercept term. And if you print these two things out, you'll see that this has two coefficients and this one just has the intercept. And now I'm calculating the mean squared error of each of them by taking the predictions of M. And then this one is the predictions of M0. And then I'm subtracting off the true value of tackles. I'm squaring that difference and summing. And now here I'm calculating 1 minus MSE over MSE0, just implementing this formula, very simple. And the number I get is about 0.01. So in this case, the model is not explaining that much variance. The difference between this model that's just predicting a constant and my regression model is not huge. That kind of makes sense because here if you look at the way that tackles is generated, there's a lot of variability. The standard deviation is 20 relative to how much explaining the predictors are doing actually. And so it kind of looks like, I'm gonna try to draw it kind of like in 2 dimensions, but so if here's the true conditional mean surface, kind of looks like almost like flat, right? It's something like this. So it's very, very, very flat. Not quite flat, but these slopes are pretty small in this direction and in that direction. And so if I just fit a constant there, it's going to do almost as good, and that's what this is reflecting. You can also do this automatically if you like. So here I'm just doing it manually to show you what this thing is, but if you just fit this model here, this M, under the hood, R actually also fits this one and then does this computation for you. So if you call summary on the summary function on your fit model, it'll print out all this stuff. Most of it you should not really look at a lot of the time. But one of the things that it'll print out is this multiple r squared, and that is what we are talking about here. And you see it's the same number. Here it rounds it, but that's the same number there, okay? R squared is just one metric, right? MSE is just one metric. Really, if you're doing prediction, you should think about what you care about, and then you should choose your metric depending on that problem. So for example, let's say you care about how often is your prediction off by more than 10%. So we're going to do a practice problem. Maybe you're predicting like insurance charges, and it really doesn't matter like if you're just trying to budget, right? And it really doesn't matter. You're going to budget conservatively. So as long as the actual charges are within 10% of the charges that are going to happen, it's not a big deal. And so you just want to count up basically how many times is your prediction within 10% of the actual value. So then instead of using mean squared error, that is taking mu hat minus y and squaring it, you want to take the average of something like this. So you just say, was this difference larger than 10% of y or not? Okay. Or maybe you're interested in the absolute error instead of the squared error. So then just look at the absolute error. Or maybe here's an example, interesting example, where let's say you're predicting a clock time. So like hours. And your regression model, however, the output is not going to be bounded necessarily between 0 and 24 hours. Maybe your regression output will give you 25 hours, or maybe it'll give you, your output might be -1 hours, because it's just a line, right? So there's no way to bound it with linear regression. And so maybe what you want to do is say, hey, if it's predicting 25 hours, then just set that to be equal to 1 hour. Or if it's 26 hours, that's 2 hours, right? So it kind of loops around. So then the prediction here is whatever the prediction is, and then divide by 24 and take the remainder. This is called modulo. That's not important. I'm just showing you that there's some cases where, and then there's some cases where the MSE is not really what you want to be doing, because maybe the predicted amount of time maybe the thing is supposed to happen at 1 a.m. in the morning, but your prediction function is predicting it's 1 a.m. tomorrow, and you don't care. That's the same. You just care about what time it happens at, right? So you want to be able to evaluate that difference in a way that's sensible to whatever your prediction problem is. So this is one possible example. So my point here is that what metric, don't always just reach for mean squared error if you actually have something that's a little bit more targeted to the problem at hand. And lastly, all of this is totally generic to regression, not just linear regression. So in all of this, I'm just looking at mu hat, right? So I just have mu hat of x here. Nowhere in here did I have any, here to demonstrate what the r squared was, but this definition of r squared, I could here, just take the MSE of mu hat, and here MSE of some other mu hat. All of this is totally generic to regression. So you can apply this in any kind of regression setting, not just linear regression. So let's do a quick problem. For this insurance data set, we're doing these two regressions. We actually already did those. And then we're answering these questions here. So I think we have that. So let's call that one M1 and M2. Okay, so if we call summary on M1, this gives me the r squared here is 0.089. And I can do the same for M2. Is that right? And 0.74. Okay, yeah. So this one is a lot better. By adding BMI and smoker, right? I've jumped my r squared from all the way from 0.08 to 0.74. So huge improvement in the prediction accuracy as measured by r squared. But what if we don't really care about r squared? What if all we care about is being within 50% of the actual charges? So let's look at that. So let's get my M1 predictions. And let's get my predictions from the second model. Oops, sorry. Okay. And let's just calculate how often the predictions were within we're within 50% of the true value, right? So, okay, we need to do like this. Right. Okay, so it's called charges, right? Cool. So here we're just, for each person, we're saying, was it or was the prediction or was it not within 50% of the actual value? So then we can take the mean of that to get the rate in which that happens. Okay, so 25, under the first model, we were getting within 50% of the true value 25% of the time. Under the second prediction model, now we're getting it 70% of the time. So also a huge improvement in terms of this metric. But you can see it's a different amount of improvement, right? Here, according to R squared, according to R squared, this looks pretty dismal in terms of prediction accuracy. But if all we care about is this this other metric, then even with this simple model that only has age in it, we're getting within 50% of the true charges 25% of the time. So if that's all we care about, maybe that's not so bad. Of course, we can improve it by adding these other predictor variables as well. So the point here is what you should be measuring in terms of the quality of your predictions. If what you care about is making predictions, what you should be measuring depends on how people are going to use those predictions.